Smart pointers, yay. Oh, getting into some spicy stuff. Okay, a pointer is a general concept for a variable that contains an address in memory. Already know that. This address refers to or points at some other data. The most common kind of pointer in Rust is a reference, which you learned about in Chapter 4. References are indicated by the ampersand symbol and borrow the values they point to. They don't have any special capabilities other than referring to the data. And of course, there are different types of references themselves. A reference is a type of pointer, and among references themselves, there are different types of references. There's a reference, null reference, and there's a immutable reference and a mutable reference. References are immutable by default. A mutable reference is a pointer to data, but also allows you to modify said data. Smart pointers, on the other hand, are data structures that not only act like a pointer, but also have additional metadata and capabilities. The concept of smart pointers isn't unique to Rust. Smart pointers originated in C++ and exist in other languages as well. In Rust, the different smart pointers defined in the standard library provide functionality beyond that provided by references. One example that we'll explore in this chapter is the reference counting smart pointer type. This pointer enables you to have multiple owners of data and keep track of the number of owners and when no owners remain, to clean up the data. Okay. In Rust, which is the concept of ownership and borrowing. In addition, an additional difference between references and smart pointers is that references are pointers that only borrow data. In contrast, in many cases, smart pointers own the data. Okay. We've already encountered a few smart pointers in this book, such as string, right? Because, yeah, that actually makes sense. I was curious of how the string type worked compared to the string literal type. Because string literal type is a pointer that literally just contains the pointer, a pointer which initially points to the beginning of the string and then the length of the string, which is how many bytes it takes up. And you can pass a string value into it as a string literal value without doing anything. You just plug it in and it works as well. That would probably be how that works, because it's a smart pointer, it will, it's smart. Instead of passing a pointer to string, it will pass the string literal instead of itself. Okay. And so string and vec's also a pointer. That also makes sense because it's an array. Strings are also arrays. Well, a string literal is an array, and a string contains a string literal. And it just gives it a bunch more functionality in Chapter 8. Although we didn't call them smart pointers at the time, both of these types count as smart pointers because they own some memory and allow you to manipulate it. They also have metadata such as their capacity and extra capabilities or guarantees, such as with string ensuring its data will always be valid UTF-8. Smart pointers usually implemented using structs. Okay. The characteristic that distinguishes a smart pointer from an ordinary struct is that smart pointers implement the deref and drop traits. The deref trait allows an instance of a smart pointer struct to behave like a reference. So you can write code that works with either references or smart pointers. That deref is how the string is able to be used as a string literal instead of the string smart pointer itself. Okay. That's actually very handy dandy. very handy dandy, because especially when you're creating a smart pointer that itself contains a pointer. Yeah, because vec not only contains the beginning as well as the length, but it also contains the capacity, right? The capacity is the total memory allocated to it, but the length is the used data. I'm not sure which it would use, like which is taking the place of what is usually. I think length. I think like like in a vector, length becomes capacity, and then there's a new parameter length, and that's the length. That is only the use space. Whereas I don't know. I'm getting ahead of myself. Um, the drop trait allows you to customize the code that is run when an instance of a smart pointer goes out of scope. Okay, this chapter will discuss both traits and show why they're important to smart pointers. So, I guess the drop trait is what allows you to manage like having multiple owners of data. It's called that ability to write custom drop code. Okay, that is useful. Okay, given what the smart pointer pattern is a Given that the smart pointer pattern is a general design pattern used frequently in Rust, this chapter won't cover every existing smart pointer. Many libraries have their own smart pointers, and you can even write your own. We'll cover the most common smart pointers in the standard library. The box, allocating values on the heap. Okay, yeah. Uh, reference count, ref mute, ref cell. Okay. That ref cell is weird. Hmm. I wonder if that might. Uh, mm, Actually, ref cell might be a way to avoid like runtime borrowing rules. Like, so if potentially solves issues in borrowing that can only be like happen at runtime and the compiler cannot anticipate. Perhaps that's how you would use it. I don't know. I'm. That's just off the top of my head. In addition, we'll cover the interior mutability pattern where an immutable type exposes an API for mutating an interior value. We'll also discuss reference cycles, how they leak memory, and how to prevent them. Okay.
Black Friday is coming early at eBay with exclusive
Okay,
offers to eBay
I'm
Plus
gonna
members starting November
okay,
15th. Don't wait, get in early for blowout deals on
15.
some of the most sought after brands. Exclusive to eBay Plus. Click or tap the banner to learn more.
Actually, this is a great way to make use of workspaces, because all of the stuff is going to be on pointers. But what if I want? Yes, I want to separate. Well, I don't need to do a workspace for that, but it would be nice. It'll be nice and structured, I guess. Eh, eh, eh. I- I'll do it anyway. And we want smart pointers. After I have to make the smart. Okay. Okay, CD smart pointers. Okay. Brucey, come here. Oh, you poor boy. What's wrong? Are you lonely? Okay. Oh, wow, that is people. Okay. Box pointers. Bum, bottom, bum. CD. Can't type. CD. Let's say, box pointer. Yeah, this entire thing is on, this entire bit is on box pointer. Yeah. That's annoying. Maybe you want to do it like that, because then it'll show up like that in there. Okay. It's binary, 18. Yeah, I also want to close that, and then that is not what I wanted to do. Okay, we get that. Okay, so, okay. So, box pointers. The most straightforward, oh wait, I still have this to do. Box dash pointer. That should just work. Bum, bum, bum. Okay. Well, we don't have that annoying issue. Okay, so the most straightforward smart pointer is a box, whose type is written box type, generic type T. Boxes allow you to store data on the heap rather than the stack. What remains on the stack is the pointer to the heap data. Refer to chapter 4 to review the difference between stack and heap. Okay, yeah. That's why you would use like box when you're returning a result for the error type, because you if you want to be able to return all errors, because um, that way like you have the space for it in memory already there. Yeah, sort of close. I don't even know if that's even true. What I just said earlier. Uh, Boxes don't have performance overhead other than storing the data on the heap instead of the stack, but they don't have many extra capabilities either. You'll use them most often in the situations when you have a type whose size can't be known at compile time, and you want to use the value of that type in a context that requires an exact size. When you have a large amount of data, you want to transfer ownership, but ensure the data won't be copied when you do so. When you want to own a value, and you care only that it's a type that implements a particular trait rather than being of a specific type. So, yeah, again, errors, like runtime errors, would be in the first and last, would fit into the first and last categories. Because, if you want to be able to return all, any error, and then handle it, outside of the thing. We'll demonstrate the first iteration in the enabling recursive types with boxes section in the second case. In the second case, transferring ownership of a large amount of data can take a long time because the data is copied around the stack. To improve performance in this situation, we can store the large amount of data on the heap in a box, and then only this small amount of a pointer data is copied around on the stack while the data references stay in one place on the heap. The third case is known as a trait object in chapter 17. In chapter 17 devotes an entire section using trait objects that allow for values of different types just to that topic. So what you learn here, you'll apply again in chapter 17. Okay, using box to store data on the heap. Before we discuss this use case for box, we will cover the syntax and how to interact with values stored within a box. Okay, so let the boxing begin. Box new, what, like 5? Wait, new. Oh. Okay, yeah. Okay. Oh. To print Allen. Yay. Turn the volume down on my headset real quick. There we go. B is equal to B. I have a feeling that if I go to cargo run -p box pointer 5. Oh, okay. So like, okay, so in terms of box implements the display trait if box probably implements the display trait, and that will itself will simply call like the display trait from the data it encloses, and that is why we can get a 5 quite easily there, because it's an ensure by default that will always work in this situation. Okay, we define the variable b to have the value of a box that points to the value 5, which is allocated on the heap. This program will print b equals 5 in this case. We can access the data in a box similar to how we would if this data were on the stack, just like any own value. When a box goes out of scope, as b does, yeah, so the good, I guess what smart point is, I guess the main thing with smart point is it's that you can dynamically change like how they work when you interact with them, depending on how you interact with them. So for example, if you're just passing a string into a function, but that function only takes a string literal, the smart pointer, that because string itself is a smart pointer, it will by itself simply provide a string literal rather than the entire string instance that it is. Same thing with box. In normal use cases, it works just like you would with the normal value. It's simply it's like forwarding. It's like if you link a file to another file. Okay. Just like any own value, when a box goes out of scope as b does at the end of main, it will deallocate. The deallocation happens for the box stored on the stack and the data it points to stored on the heap. Putting a single value on the heap isn't very useful, so you won't use boxes by themselves in this way very often. Having values like a single I32 on the stack, where this works. Having a single I-32 on the stack where they are stored by default is more appropriate in the majority of situations. This will be a case where boxes allow us to define types that we wouldn't be able to if we didn't have boxes. Okay, so at compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type, where a value can have as part of itself another value of this as part of itself another value of the same type. Because of this, nesting of values could theoretically continue infinitely. Yeah, that's in fact actually using a box. I know this. I've seen this before. You can use a box to create a dynamic array. Dog! I'm right here. I will give you cuddles if you come here. He's not coming here. He doesn't want my cuddles. I'm now depressed. My dog doesn't like me.
Emerge from lockdown with a surge of live music.
My dog would rather screech at a gate than let me give him pats. Yeah. That I'm gonna wait till this ad's over until I talk again.
Kick on after hours at the Melbourne Music Week Club. Ready to
Okay. So, at compile time, Rust needs to know how much space a type takes up. One type whose size can't be known at compile time is a recursive type. There are where a value can have as part of itself another value of the same type. Because this nesting of values could theoretically continue infinitely. Rust doesn't know how much space a value of a recursive type needs. However, boxes have a known size, so by inserting a box in a recursive type definition, you can you can have recursive types. Yeah, so you cannot have a recursive type unless you use a smart pointer, usually box in this case, because it literally just contains a value of anything. Yeah, so if you wanted to have, like, I don't know, like a point, right? Like a vector, but you also wanted to contain, say, like, it's a vector, like a normal, right? A vector normal. Like you would, that would also be a vector, but that would be stored within a vector and stored within a vector, which could continue theoretically infinitely, because it's in the data type itself. But if you use a box, you can essentially you have full control over that recursion, because you can just not put a value in the box, because the box has yeah. Anyway, explore the cons list, which is a data type common in functional programming language. As an example of a recursive type, the cons list type will define is straightforward except for the recursion. Therefore, the concepts in the example will be useful anytime you get into more complex situations involving recursive types. More information about the cons list. A cons list is a data structure that comes from the Lisp programming language and its dialects. In Lisp, the cons function, short for construct function. So it's a constructor. It's a constructor function. Okay, constructs a new pair from its two arguments, which usually are a single value and another pair. These pairs contain pairs. These pairs containing pairs form a list. Okay, I guess that's one way to do a list. Well, I mean, a list of dynamic size. Anyway, it would be a list of dynamic size, because you could continue adding to it infinitely. Right, so like, Vecton's function concept has made its way into more general functional programming jargon. To cons x onto y informally means to construct a new container instance by putting the element x at the start of this new container, followed by the container y. Okay. Each item in a cons list contains two elements, the value of the current item and the next item. The last item in the list contains only a value called nil without a next item. A cons list is produced by recursively calling the cons function. The canonical name to denote the base case of the recursion is nil. Note that this is not the same as null or nil as the null or nil concept in chapter 6, which is an invalid or absent value. Programming languages use cons lists frequently. The cons list isn't a commonly used data structure in Rust. Most of the time, when you have a list of items in Rust, Vec is a better choice to use. Other more complex recursive data types are useful in various situations, but by starting with the cons list, we can explore how boxes let us define a recursive data type without much distraction. Okay.
Creepy animals! You're not gonna get 5 yards.
Grab him! We're going back to the outback.
We got some deadly creatures to hunt.
I've never had a pretty friend before. Can I wipe my bottom with your fur? What?
Dumbass.
The outsiders
Enum? Oh, okay. Enum. List. Okay. I understand what's happening. I didn't read it earlier. Like, I read it as a struct, cons. 32 and a list next. And then nil. This. Okay. Note we were implementing a cons list that holds only items for the purpose of the symbol. We could have implemented it using generics as search option to define a cons list type that could store values of any type. Using the list type to store the list 1, 2, 3 would look. I know how to make this into like a macro, well, sort of. I'm terrible at macros. I do not understand them enough to actually do that, but I could give it a shot. Not going to. It's too hard. I am not one for unnecessary difficulty, unless, well, not including the times where I am one for unnecessary difficulty. The first cons value holds 1 and another list value. The list value is another cons value that holds 2 and another list value. This list value is one more cons value that holds 3 and a list value, which is finally nil. The non-recursive variant that signals the end of the list. Okay, yeah, so because this is recursion, we're not using the like box pointers here. We could what was it? Let's list equal cons cons what 1 cons 2 cons 3 and nil. I believe, yeah, it shouldn't even like yeah, there you go. Oh, duh. Okay, well, first of all, we need to actually make it so that we can access cons and nil directly. Use we don't have to put crate here. I believe I can just put list con yeah cons no. Okay. And now we have, yeah, see, it immediately tells us, hey, use a box, not a recursive. Yeah, so you need, essentially, you need to redirect the recursive into something where we can know the finite size of. Theoretically, it can go forever either way, but one way we have control. Yeah, anyway. Blah 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 blah. Error shows this type has infinite size. The reason is that we've defined list with a variant that is recursive. It holds another value of itself directly. As a result, Rust can't figure out how much space it needs to store a list value. Let's break down why we get this error a bit. First, let's look at how Rust decides how much space we store in a non-recursive type. Recall the message enum we defined in when we discussed enums in chapter 6. Vaguely, probably. Not really. Determine how much space to allocate for a message value. Let's go through each variance to see which variant needs the most space. Rust sees that message quit doesn't need any space. Message move needs enough space to store two values and so forth. Because only one will be used, the most space a message value will need is the space it will take to store the largest of its variants. Bruce, come here. Contrast with this, what happens when Rust tries to determine how much space a recursive type like the list enum in 15.2 needs. The compiler starts by looking at the cons variable, which holds a value of type i32 and a value of type list. Therefore, cons needs an amount of space equal to the size of i32 plus a list. To figure out how much memory the list type needs, the compiler looks at it's infinite. Yeah. Rust can't figure out how much space to allocate for recursively defined types, so the compiler gives an error. The error includes this helpful suggestion. Ooh, look at that. In this suggestion, indirection means that instead of storing a value directly, we change the data structure to store a value indirectly by storing it in a pointer to the value instead. Yeah, okay, where was I? I looked away, now I forgot where I was. So, because a box is a pointer, Rust always knows how much space a box needs. A pointer size doesn't change based on the amount of data it's pointing to. This means we can put a box inside the cons variant instead of another list value directly. The box will point to the next list, the cons variant, the next list wait, what? the box will point to the next list value that will be on the heap rather than inside the cons variant. Conceptually, we still have a list created with lists holding other lists, but this implementation is now more like placing items next to one another rather than inside one another. That's a good way to explain it. We can change the definition of the list enum in blah blah blah, and we can fix it. I am not even going to look at that. I'm just going to use my brain, my ginormous brain. So I want to remove this. We want to change it to a box of type list. Guys, I think I did it. Oh, except for here. Right. We just okay, so let's list equal cons
Hi,
1
streamer,
and
content creator, and winner of the
box
2020 Gamers Awards. Streaming on Facebook
colon
Gaming has
new
connected me with viewers from around the world and has
cons
given me the platform to build a
2
positive community through the games I love.
box
What will
colon
you create?
new
Go to fb.gg/creator
cons
or tap the banner below to
3
get started.
box so if I redo it now, it should be just fine. Yeah, look at that. Amazing. Not really. The cons room, blah 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 blah. Yeah. Box provides only the indirection and heap allocation. They don't have any other special capabilities. Like those we'll see in other smart pointer types, they also don't have any performance overhead that these special capabilities incur, so they can be useful in cases like the cons list where the indirection is only a feature we need. We'll look at more use cases for boxes in chapter 17.2. The box type is a smart pointer because it implements the deref trait, which allows box values to be treated like references. When a box value goes out of scope, the heap data that the box is pointing to is cleaned up as well because of the drop trait implementation. We'll explore these two traits in more detail. There's two traits. These two traits will be even more important to the functionality provided by the other smart pointer types we'll discuss in the rest of this chapter.